Presented by Caltech.
Again, we come back to the theme of transitions. Ahmed's talk this morning is about the transition in matter, dynamics between matter and motion. And we talked about transitions politically in Egypt and how difficult that is, and now transitions in the economy and technology, and the race that's on between rapid technological change and governance, stalled governance. Governance in the end matters whether you go forward or backwards as a society, and you can catch up with the technological change. Now we're going to shift to a completely different subject, outer space and space exploration. Our speaker is known to everyone here in the local community. Charles Elachi has been director of Jet Propulsion Laboratory since 2001 and responsible for all of the, I should say most, of all of the exploratory probes of our galaxy in recent years. He has been a principal investigator on research and development studies and flight projects sponsored by NASA, including the Shuttle Imaging Radar, the Magellan Imaging Radar, and the Cassini Titan Radar. He's author of over 230 publications in this field of microwave remote sensing. He's taught physics here at Caltech, excuse me. I gather those aren't Cal State people who are laughing. Most importantly, not most importantly, but most uniquely perhaps, he has an asteroid named after him. In 1998, I forget when, I think, 1989, I guess, asteroid 1982 SU was renamed 4116 Elachi in recognition of his contribution to planetary exploration. So today, Professor Elachi is going to fill us in on what he's learned in all his years at Jet Propulsion Laboratory and space exploration, and even said he would talk about whether there's life on other planets, which is the question everybody always wants to know. Professor Elachi, please.
First, I want to apologize for my voice. About 6 weeks ago, somehow it disappeared. The doctor didn't see any problem with it. And he said, your problem is that you talk too much. And that the only solution for you, stop talking for a while. Unfortunately, I'm failing miserably in doing that. I couldn't miss Ahmed's, event today. Before I give my talk, I was reflecting a little bit about what Ahmed said about the uniqueness of Caltech. Now, I'm assuming most of you would know, but just in case you don't, here we have this small school in Pasadena that the government, NASA, has entrusted basically to oversee JPL, the premier organization to explore space. A school of 200-300 faculty really overseeing our nation endeavor of exploring the solar system and the universe. That's pretty amazing when you see that. So that's one thing more to add to the unique things that Caltech, does. So what I'm going to do is kind of to describe a little bit what we expect will be happening in the future of space exploration. But I thought to reflect on that, I would like to give you a quick overview about how the universe came about. Now, I want to apologize to my astronomy colleagues here. This is a very simplified history of the universe, so no grading, today. So basically what we know is somehow around 13, 14 billion years ago, there was a Big Bang which occurred over a fraction of a second. So it was very accurate, Dr. Phillips. It was a very accurate clock which happened at that time. And literally zillions of particles formed. Somehow these particles got together and they formed stars and galaxies. And even today, we are seeing galaxies which are interacting, new stars which are forming, stars which are disappearing. And if we focus on one of these galaxies, that's what it looks like, literally billions of stars in a galaxy which is very similar to our galaxy. And somehow these particles got together and they formed planets, like our planet, solar system. And somehow these particles got together on one of these planets, which we call Earth, which had the right condition, the right environment, the right temperature, which led to the formation of cells. And somehow these cells got together, and after almost 4 billion years of evolution, they formed the beautiful world that we're in. When you think about it, it's absolutely amazing. How did it start from those particles? And here we have this beautiful world which is around us. And the most important part is after all that evolution, we got Ahmed Zewail. So Ahmed, you didn't appreciate it took 3.8 billion years to get you here. So the key thing, what we're trying to do in our space exploration is to understand how did that happen? How does the universe work? How did the planets form? How did life evolve? And is life common? Is there only one Ahmed Zewail, or is there billions of Ahmed Zewail, around the universe? So now I'm going to describe to you some of the things we are doing in that endeavor. People always ask me, in the next 20, 25 years, what will be the most exciting thing that we'll be doing in space exploration? And I told them, at least from my perspective, there are 4 areas that I'm going to describe to you today, which I think will happen in the next 20, 25 years. Let me start first with the exploration of Mars. Mars is one of the nearest planets to us. Venus is the other one. And Mars has a lot of similarity, but a lot of differences with Earth. If you look at the surface of Mars, it's about the same as the land surface on Earth. It's a pretty big place. Mars has polar caps, similar to the polar caps we have on Earth. They expand and shrink depending on the season. Mars has an atmosphere. When you look more in detail, Mars has canyon, similar to the Grand Canyon here on Earth. Mars has volcanoes, the same way we have volcanoes here on Earth. Matter of fact, Mount Olympus on Mars is the largest volcano in our solar system. It's extinct today, but at some time in the past, it had all the dynamic which formed that volcano. If you look at the surface on Mars, it looks very similar to the surface in Owens Valley. Usually I used to give a test to my students, guess which one is Owens Valley and which one is Mars. And to be honest with you, I can't tell the difference. I forgot which one, is which. So the point I'm trying to make is that geologic activity which is happening on Mars is very similar to the geologic activity which happened on Earth. So one day when an astronaut will land on Mars, she will think she's landing in Owens Valley. But to tell you what we have discovered so far, one of the key things we have discovered through all our spacecraft and rover is that sometime in the past, Mars used to have oceans, similar to what we have here on Earth. But because of the climatic change on Mars, that water either froze or some of it escaped into space. But now when we look at Mars, particularly in walls of craters, actually we see what looks like flow of liquid, which is happening from just below the surface as the ice is melting. And actually we see a liquid coming on the surface. Now that liquid doesn't stay for long because the pressure on Mars is much lower than the pressure here on Earth. But clearly liquid exists as a result of ice which is below the surface. Now, to give you a feel of the challenge of exploring planets like Mars, I thought I'll give you at least one example of the challenge. So when we sent our rover a few years ago to land on Mars after 225 million kilometers, we had to land within a 2-kilometer area. Now, to give you a feel what that means, that's the same as if you go outside and hit a golf ball towards St. Andrews, and the golf ball have to go straight in the cup. That's how accurate we have to do that. And just to make it a little bit more challenging, the cup is moving at 60,000 miles per hour. So that adds to the challenge. So that's kind of the illustration, one illustration of the challenges that we have in order to explore, Mars. Now, what do we have on Mars today? We have 2 rovers. One of them has been operating for 12 years on the surface of Mars. Just imagine, for thousands of years, our ancestors looked at that red planet and wondered what's on it. And here, our generation, we put our footprints on that planet through the rovers that we have on it. And we have been there for 12 years, day in, day out, exploring that planet. So now what I thought I'll show you, I'm going to show you a short video about the landing of Curiosity on Mars. And that's not to show off, but for 2 reasons. One, Ahmed was at the landing at JPL. But more importantly, is to reflect, what you will see will reflect of what Ahmed says when people ask him about the secret of success. He touches on a couple of things. He says it's passion, it's optimism, it's prepared mind, and the sky is the limit. And you are going to see those 4 things in the eyes and the reaction of the people who are at JPL and around the country watching that landing on Mars.
Things are looking good. Coming up on entry. Vehicle reports entry interface. At this time, it will begin pressurizing the propulsion system to increase the thrust of the system. We'll use that for all the maneuvering in the atmosphere we're about to do. We are standing by for guided start of guided entry. We are beginning to feel the atmosphere as we go in here. The vehicle has just reported via tones that it has started guided entry. At this time, the vehicle is beginning to steer its way to the target. We have seen peak deceleration. It is starting its first bank reversal. It is reporting that we are seeing G's on the order of 11 to 12 Earth G's. Bank reversal 2 is starting. We are now getting telemetry from Odyssey. We should have parachute deploy around Mach 1.7. The parachute is deployed. We are decelerating. Speed chill has separated. We're found the ground. We're down to 90 meters per second at an altitude of 6.5 kilometers and descending. Standing by for back shell separation. We are in powered flight. We're at an altitude of 1 kilometer descending. Standing by for sky crane. Sky crane has started.
Signal to us, you remain strong.
Touchdown confirmed. We're safe on Mars. Curiosity will take us.
Got thumbnails.
Today, right now, the wheels of curiosity have begun to blaze the trail for human footprints on Mars. This is an amazing achievement.
Well, today on Mars, history was made on Earth. The successful landing of Curiosity marks what is really an unprecedented technological tour de force. It will stand as an American point of pride far into the future.
Well, tonight was a great drama that was played. I could only think of the words of Teddy Roosevelt as I was sitting there. It is far better to dare mighty things even though we might fail, than to stay in the twilight that knows neither victory nor defeat. Needless to say, that required a that required a lot of passion and a lot of optimism to make these things happen. Now, just to give you an idea, there were 50 million Americans on our website, that evening. Now, when I go to Washington, I tell them there were 50 million voters, and that gets attention, on the Hill. So as I mentioned to you, not this rover, but the previous rover has been now operating on Mars for literally 12 years, basically exploring day in and day out. And it keep on going. It was supposed to work for 90 days, then for 9 months, then for a couple of years. David, remember, he was at the landing there, and 12 years later, it's still working. Just imagine how many of you have a car that you use every day for 12 years, and you don't have to take it to a garage, to kind of fix it. But what came from all of this, as I mentioned earlier, these are pictures which were taken from Curiosity, a while ago, and that's what looks like dry lakes for many people. So it's not exactly, but very similar to when I go to the Owens Valley. And as we travel, we actually go and make direct in situ measurement. We actually drill through the surface, take the material, and basically run it through a chemistry lab, which is on the rover. It has X-ray, it has machines, it has a gamma ray machine, it has a mass spectrometer, it has a laser system which evaporates the surface to look at what material are being emitted from it. And what we found is that everything, all the elements which are in your body actually exist on Mars. The phosphorus, the oxygen, the nitrogen, all the material that we have on Earth here actually exist on Mars. So the key question is, if we had oceans in the past, we have all the right ingredient, could have life started, on Mars. And that's the key objective we're trying to do in our exploration on Mars. We have not detected organic material. We have not detected living material. We have detected organic cells, or organic molecules. But our goal is to be able to explore and find if life ever existed on Mars. This is where we are about a week ago. You see these big sand dunes in front of us. We are now driving around those sand dunes so we can get on those hills where you see all these layered rocks. And as we analyze them as we are going up the hill, basically that would tell us about the history of what was happening on Mars. As you could imagine, you don't need to be a geologist to kind of appreciate that the bottom layers are older than the layer above it, which is older than the layer above it as they accumulate in that location. So now, what we are doing in the next 10, 15 years, the next major step is basically to take a rover which will drive around, look at the interesting samples, collect those samples in sample holders, put them in a certain location so we can go back and bring those samples back to Earth and actually do a much more detailed analysis of those samples here. That could be done or will be done in the middle of the next decade. And to make it more fun for that mission, we're adding a little helicopter to it. We don't have final approval yet, but we're almost there. That helicopter which will go and fly in front of the rover and actually survey the area and guide the rover of where to go to interesting location. And some of the advances in technology are going to allow us that literally all the people involved anywhere around the world would put the glasses and basically transpose them as if they are with the rover on Mars, and be able to communicate with them and geologists as if they are in the field. And once they decide to do something, they will say in words we want to drill here, then the commands will go up to the rover, and the rover will move and drill in that location. So that's the kind of technology we'll be using in our exploration. And all of this is leading to what I believe in about 20, 25 years of actually having long-term station on Mars, similar to what we have in Antarctica. They'll be mostly robotic, but on a regular basis, actually human can go and visit, those stations. Now, I assume many of you have seen the movie The Martian. Now, I like that movie a lot for a couple of reasons. One, it's very good about JPL. It reflects the JPL director, kind of okay. But more importantly, I think our kids could be doing that. I think it's possible during our children's lifetime that actually humans will be going to Mars and doing that exploration. So that's what I think will be happening on Mars in the next 20, 25 years. Now let me move to the second topic, and that's what we call exploring other oceans. What we have discovered in the last decade, that actually liquid oceans of H2O are more common in the universe than we thought. If you look at Europa, which is on the left, which is a satellite of Jupiter, we believe that actually there is an ocean below that ice. If you look at Enceladus in the middle, which is a satellite of Saturn, you see those geysers shooting from Enceladus. And actually we had our spacecraft Cassini fly through those geysers, and they are made of H2O with salt with them. So the belief is actually there is an ocean, below the surface and actually shooting, those geysers. Now, how could that happen? That's very far out in the sun. It's awfully cold. Well, these satellites are in orbit around giant planets, and as their orbit is slightly elliptical, you get tides. And the tides actually is pumping that satellite day in, day out over millions of years, and that melts the ice and keep it warm below the surface. On your complete right, that's Titan. And what you are seeing are large lakes, like the Great Lakes in the US. And what we see on Titan is actually rain which comes down, goes into rivers, goes into these lakes, evaporates, goes into the atmosphere. So we have a complete cycle, except it's not water. It's all made of methane and acetylene and organic material. So the question is, could the life evolve in a different environment than on Earth, in an organic kind of environment? So these are the kind of things that we're planning as we speak to go and explore. The most immediate one will be Europa. As you can see in the picture, you see all this fracturing, and we believe that there is actually a deep ocean, just a few hundred meters to possibly a few kilometers below the surface. And that ocean is almost twice the size of the total amount of water here on Earth. So what we're planning to do by the 2021-2022, we're in the early stage of designing missions which will actually go and map the surface of Europa, use radar to sound the ice so we can determine how thick it is, put a lander, like you see on the right, to determine the property of that ice and how hard it is. So in the future, we can plan to land, melt our way, and get down to that ocean and see if there is life, in that ocean. So that's the kind of thing that I think the young kids who are sitting here probably will be working on in the next 15, 20 years. Now let me move to my third topic, which are exoplanets. 15, 20 years ago, we had no idea if there are planets around those billions and billions of stars which are in those billions of galaxies. Today, almost every star we look at, we actually see planets around it. Now, how do we do that? So actually, we look at the star, we look at its brightness, and see if there are every once in a while a dip in that brightness. And if that dip is periodic and regular, that means an object is coming in front of it and blocking a little bit of light. And if we look at the periodicity of the dip, that tells us what the period of the planet, how deep the dip is, tell us how big the planet is, because the larger, the bigger a dip is occurring. So we're finding that actually almost every star has planets around it. And so far, we have literally discovered thousands of those planets. As you will see in this case, we have 1,937 exoplanets which are confirmed. That means they were observed from the satellite and from the ground, so we have independent, observation. And what you see, those posters, is we have a group of artists at JPL who sat down and tried to imagine what would life be on those planets. So you see the one completely to the left, just to illustrate one or two of them, completely to the left is a planet around a cold star. So the belief is that most of the radiation is in infrared, so the grass will look red. So we'll be talking about the grass is redder on the other side of the fence, not greener on the other side of it. Requires artists to imagine that. If you look at the one next to it, that turned out to be a planet which is not around a star. It's just floating by itself, so it's always dark. So the idea is people on that planet will be partying all the time because it's night all the time. So now the next step, what we want to do in the next 20 years is not only detect the planet, but actually start imaging them. And the way we'll image them is by using a coronagraph. It's very simple. I barely can see you because the light is shining in my face. If I block it here, man, you look a lot prettier than I thought. So that's exactly what we're going to be doing. By taking a coronagraph, blocking the light from the star, and be able to look at the light coming from the planet themselves. Now that requires some very advanced optics to be able to do that, because the planet is 1/1,000,000th the brightness coming from the star. So you need very accurate optics to actually do that. But that's possible. We are developing the engineering. And over the next 10 to 20 years, when you come to a conference like this, we will be able to show you what I call the family portraits of the neighboring few thousand planetary system close to our planet. And these are some of the techniques that we're flying. Matter of fact, the first one, which is a W-FIRST, that will be launched in 2024, only 8 years from now. Now, the fourth topic I talk about, the advances, is looking at our own planet, which is probably the most important one. This is one of my favorite pictures. This is a picture taken by the Cassini spacecraft when it was on the other side of Saturn. And the sun is behind Saturn, so it blocked it. So you can see some faint object. And you see there is something at the bottom right, that little dot. Guess what that is? That's Earth. That little teeny dot, that's us. That's all of us, all the people you like, all the people you don't like. They are all living on that little planet. So it's important that we take a good care, of that planet, because the only thing we have, at least for now. So let me tell you about some of the advances we are looking at of how can we manage our planet or know about how to manage our planet in a more conscientious way. With some of our satellites, we are literally monitoring the ocean rise. The ocean is actually rising. Some people might be skeptical about it, but science gives us direct measurement. See at the bottom right, over the last 20 years, we measure the height of the ocean by using what Dr. Phillips talked about, so GPS satellites that allow us to locate our satellite very accurately. We measure the distance with a radar, and we can reference down to centimeters the location of the ocean surface on the average of it. And the ocean has been rising because the temperature has been increasing and expanding the ocean. But in addition to the expansion, the increase in temperature have been melting ice in Greenland and Antarctica. And what you see at the top right is the amount of mass which is in Greenland, which has been decreasing. It oscillates during the season, but on the average is decreasing. Now you say, well, how in the heck do you measure the mass of the ice? Well, we weigh it. Now you say, how in the heck do you weigh it? Well, we measure the gravity field just above Greenland and measure it very, very accurately. And by monitoring it, we can see the change in the gravity field, which tell us how much mass is being lost. And the way we measure the gravity field is a very ingenious way. You take two satellites following each other, you measure the distance to a fraction of a centimeter. So when the first one comes and feels the gravity area, if it's a little bit an increase, it speeds up. And if it's a decrease, it slows down, and the next one catches up with it. So by measuring the distance very accurately, you can actually deduct the gravity field very accurately. And we measure it so accurate that we can determine how much water there is in the water table. This is in the Central Valley in California. And as we were watching it over 12 years and the drought coming, there have been less and less water in the water table. And we have been able to measure the change of the water in the water table below the surface. Because gravity, you don't need to see it. You can feel it even below the surface. And we can measure changes in the water table of 1 centimeter. So a decrease of 1 centimeter actually changes the mass enough that we can detect it, from space. So now we are developing satellites which basically will allow us on a global basis, on a continuous basis, monitor the availability of water, be it in the water table or be it in the Sierras or the equivalent, in the snow. Because as the snow melts, also you are losing, mass from that location. And we can determine the amount of water which actually exists in the Sierra and when it actually will melt. Another major advances we are doing is by measuring surface motion now down to a centimeter. And the way we measure it is we take a picture using radar instrument, and then we come the following day and take a second picture. And by combining the two coherently, we actually create fringes. That's a famous Fresnel fringe experiment. So that's exactly what we're doing. So if an earthquake happens in between, actually we can measure every little motion which occurred from that earthquake. So what you are seeing here on the left is the earthquake which happened in Napa Valley. And by going from one blue color to another blue color, that means the surface moved by 1 centimeter. And the benefit of it, other than the geophysics and understanding the earthquakes, is you look at the area where the fringes are very close. That means there have been a lot of motion. And that means the area which is the most damaged, and that's where you'll send the rescuers, very quickly. And this technique was actually demonstrated in the latest earthquake in Nepal, where literally within hours, we were able to tell the rescuers where there was the most motion which occurred and most likely the most damage which have occurred. And the same kind of technique we're applying to look at volcanic motion and volcanic eruption. So on a regular basis, in this case, we're monitoring the Galapagos volcanoes, and you see the side of volcanoes as they are inflating, as lava is moving below the surface. It's the same thing we see in Mount Etna and in many of the volcanoes around the world. So this capability also over the next few years will have operational capability which will monitor these motions day in and day out. And not only monitoring them, but you'll have them in apps on your iPhone. So it will be everybody around the world can have access to the information about what's happening, to our planet. So in closing, I want to repeat what Ahmed said. It was the passion for science that supplied the energy, and it was optimism that made almost the impossible possible. That's the kind of things we do at Caltech day in and day out. And Ahmed, you have been a model for all of us, and that's what we dare. Mighty thanks. Thank you very much, and happy birthday.